to store to the body of the person when the organs is too sick to do their job. So this is man-made. So now we're going to go in the deep what the man-made did and how it going to works, and we're going to comparison what are the components using, what is the comparison of the natural lung and with the artificial lung, what is the life of the natural lung and what is the life of the man-made. So this Ecmo actually buys the time until the native heart or lung recovers within 2 weeks. So actually the target of the Ecmo is to buy the time. Meantime, the intensivists, the nurses or the light health professionals working with the patient having the sick lung or sick heart. So the time we are getting, actually we are buying the time. So the heart or the lung can recover. We'll talk about the lung. So lung recover. So actually this is the time by the Ecmo procedure. It can be the destination and it can be the bridge to transplant. So nowadays we are doing the bridge to transplant. Even we are doing the transplant, lung transplant, and very soon we are going to start the heart transplant, which is in action, and we are having a few cases already going to be discussed and going to be operated soon if the issue is the donors is happy to donate the heart. It's very difficult. So see, this is your native heart and this is the pump. What is the correlation of the pump of the heart? The role of the heart is to pump, the pumping. So what we are doing with the roller pump, we are pumping blood to the body. We are getting blood, sucking blood and returning back to the body. So we are replacing the function of the heart, and there is two type of pumps. There is two type of pumps. The pump which I show you is the roller pump, where we need to have piece of tube with the angles. They push the blood toward there. And this is the centrifugal pump. So actually we have two type of pumps. The pump which is using in the Ecmo is your centrifugal pump, and it is preload and afterload dependent. This is preload and afterload dependent, but the roller pump is not a preload and afterload dependent. So this is the reason we are using the roller pump in a heart surgery, and we use the centrifugal pump mostly for the long-term bypasses like an Ecmo or left hand bypass or LVAD or BIVAD or RVAD. So normally the pump which is going to be used is the centrifugal pump, and it is preload and afterload dependent. So we talk about the heart, now we are going to talk about the lung. So lung's function is to oxygenate, ventilate, as we already get to go through with that. So we are replacing the function of this organ with man-made organ. Okay, so sorry. So what the things we required for the man-made Ecmo? We need, of course, we need disposables, we need non-disposables. So what are the disposables? Of course, we need catheters. There's two type of catheters. One is the access catheter, and the other one is the return catheter. The blood which is sucking from the body through the access, and the blood which is returning back to the body through the return cannula. So then we have the disposable cannulas. We need heart machines. Nowadays, this is your Ecmo machines. Before it was a huge machine. Now this is your Ecmo machine. It's very portable and friendly user, compact machine. All features buttons like a pre, post, TMP, temperatures, online hemoglobin hematocrit. So everything was in a small machine which can be lifted by your single hand. But the heart-lung machine was not possible to lift it by a single hand. So then of course to maintain the oxygen. So how can we oxygenate, how can we provide oxygen to the body? Through the air mixer blenders. Like normally in a ventilator, you have the ventilators, but now your ventilator is not enough for the patient's lung. So now you need something which, because this is outside the body, to To outside the body, you need to oxygenate. You need to provide the oxygen. You need to remove the CO2. So this is called the Securitized air mixer blender. So with the help of this, we maintain the oxygenations of the patients outside the body. And this is your warmer to keep the temperature normal. Normally, when you're going to take the blood outside the body, it's going to be hypothermic. So to maintain the temperature, we need a warmer. So of course, we're going to talk about the PVC, the tubings. So without these tubings, this is the tubings. This is the oxygenator. From this, it is connected with the patients. So we suck the blood through the patients. They're coming into the oxygenator. From the oxygenator, coming back to the patients. The beauty of this tubes are, this is bio-imported PVC tubes. We are not, the material we are using is a PVC, it's a polyvinyl chloride material. It is bio-imported with aluminum adherents, which increases biocompatibility of the Ecmo circuit, and the lifespan of the circuit is around 30 days. This is by the manufacturer, but it can go more than 30 days. It's not mean that after 30 days you are going to remove, but it can be less. It's not that the manufacturer mentioned this is 30 days, so it will go to no. It depends on the patient's physiology and hematology. It may be going to be change the circuit within 1 day or within 2 days. Or it can be go for like 2 months, so you don't need to change the circuit. So actually the lifespan of the circuit and oxygenator is like 30 days. See. So normally there is two type of cannula we are using. The first cannula we are using is the access cannula. Access cannula is a multi-hole cannula with a reinforced. There is less chance to be kinking in case of mobilization of the patient. So this is a reinforced long catheter like a 60 centimeter with a multi-hole, so that we can suck more volume from the body to the oxygenator. And there is a less chance for the kinking because the reinforced, and the positioning of the IVC cannula is within the hepatic IVC if you are going to cannulate the patient for the femoral. So if your Ecmo, normally we are doing the Ecmo like a fem, so for your IVC, your access cannula going to be insert for the femoral vein, and it is going to within the hepatic IVC. It should not go above than the hepatic IVC. So to reduce the recirculation, that we are going to study the recirculation later on. But now the IVC cannula or access cannula is using to suck the blood from the body into the oxygenator. Why we never say venous cannula? Because in the term of the IVC access cannula, in a cardiac surgery we used to say venous and arterial cannula, but here we can't say the venous or arterial because this is something we are doing the VV Ecmos. So never say that this is venous cannula. You are going to confuse to yourself and to the team members. So better to use the term access and return. So this one is your return cannula. Return cannula will go very far because I think can go 50 centimeter length, having the few holes. This cannula is not a multi-hole. It's having few holes on the tip actually, because we don't want a multi-hole. Otherwise there is chance of recirculation. So we always go with the cannula having the hole only in the tip, not the multi-hole from the long. No. And then this is thin hole, and of course this is wide for the position of this cannula is within the right atrium. The difference of the positioning of your access and return is around from 8 to 10 centimeter. So if it is less than 8 to 10 centimeter, there is a chance of recirculation. So you, instead of providing oxygenated blood to the body, you are taking back to the system, and you will see in your parameters, your SpO2, your saturation is the highest, your SpO2 is the higher side. So the color of the tubes are the same, but the patient side, the patient you will find maybe desaturated patient is not stable. So of course, how you will check by with the Ecmo, with the X-ray, you have to position your cannula. If your return cannula is within the right atrium, your access cannula is within the yes. Thank you so much. And it is about 8 to 10 centimeters below the access cannula. So this one is actually the. If we were going to check, this is your access cannula. This is coming this one. So we are sucking. This is the pump, this is the motor which is helping to suck the blood, and with the air mixer blender we are oxygenating, providing oxygen and removing CO2 with the sweet gas, and here the oxygenation take place and then return back to the water. with the flow dynamics. We are going to talk about the flow dynamics. So see how the blood is coming, going back, and see the change of the color because of the flow. We suck blue blood. We suck blue blood from the body, and we provide oxygen through the air supplemented with the oxygenator with the specific, and with the pink blood or the red blood, oxygen blood is going back to the tissues. So in this, we are monitoring three pressures are very important for the ECMO. Whenever you initiate ECMO, always consider your three pressure is very important. If you ignore these three pressures, there is a chance in the mid of your shift you can maybe lead a disaster. So what are the three main pressures? Number one pressure is your excess pressure. Why we are focused on excess pressure? Because when we sucking blood from the body with the kinetic force, with the magnet, with the coupling of the motor, we sucking with a higher RPM, there is a chance of shear rate increase, shear stress, and it can lead the destruction of the cells, and you will find a hemolysis mostly. So you have to maintain the flow and the pressures within the normal range. So excess pressure is very important. Sometimes your patient is a hypovolemic, you are sucking more, and which can lead for cavitation, and you can make a embolism. The ear, this is the earlock will come up. You will not good chance to flow, return back the flow to the patient. So the excess pressure is your P1 pressure is very important. Number two is your P2 pressure. P2 pressure is your pre-membrane pressure, and pre-membrane pressure is higher than your post-membrane pressure. Anyone answer why? Yes, there will be the pressure. So this is the reason P and P3 difference is your TMP pressure, which after you will get a resistance here. So if you are, for example, 150 pressure, with the resistance, your pressure will be something like here is 150 and 130. So 20 will be the delta P, transmembrane pressure, and transmembrane pressure is the pressure who will lead you, who guide you, your membrane is failing or it is okay. So ideally your TMP pressure should be the double than your baseline. It should not exceed more than 50 millimeter per mercury. So we already talked, so I am going to go through excess, pre, post, transmembrane. We already talked, so we need to go. So see, what is the ideal negative pressure? What is the ideal negative pressure? 6 That's it. What should be the ideal negative pressure on excess pressure? Actually, the ideal negative pressure for the ECMO is minus 60 millimeter per mercury. But normally, the cut down for the excess pressure is minus 100 millimeter mercury. But if it is go beyond than the minus 100 millimeter per mercury with the higher RPM, there is a chance of suctioning and to increase the shear stress, which can regulate your destruction of the cells and hemolysis. So it should not go more than the 100. If it is more than 100, you have to reduce the RPM, or either you have to dilate your patient and increase the volume. It's not bad only to reduce the RPM. Sometimes you need a higher flow. So what you can do, you can increase your, you can go through with your CVP line. If the patient still need a volume, you give some volume and dilate the patient and keep it the same and just decrease your excess pressure. See, if the patient have less volume and you are having the higher RPM there is a chance of chattering. Chattering means the fluctuating of the excess line. It means there is less volume, the space of the tube is bigger. Either you need to decrease the tube or either you have to increase the volume of the patient. So the chattering can lead the cavitations. So what you can do is you have to reduce the RPM. So what are the reasons? So these are the reasons. Number one, hypovolemia. Number two, less sedation. Sometimes your patient is awake. Number three, shivering. mobilization and kinking with the tube or partial kink of the tube. This can be done. This is not only the hypovolemia. So if you are the bedside nurse or as a physician, if there is a higher RPM, a higher access pressure, don't go directly to give the volume. First you need to go through with all these steps. Is there is a patient ready the hypovolemic or not? Is the patient properly sedated or not? Shivering, mobilization, thinking of the tube. So go through with it. Sometime your height, your machine's height is matter also. The type of transportation you will find the higher access pressure because machine need more power to suck and the patient is on the lower side and your machine is on the upper side. Positioning of the control is also. So if you ignore all this, there is a chance of cavitation and cavitation lead for aneurysm. So I will discuss if your EMP is more than 50, you need to change your oxygenator and then go with your gas transfer formula and equations. Okay? So you will find, see, this is the reason of a EMP increase, resistance and because of the blocks. So you have the daily inspection, check your oxygenator and find if there is any clots. Normally this is always go to the and share the report that there is a clot formations or febrile formation in the oxygenator. It is going to relieve the fail of your oxygenation or failure of the oxygenator or you need to be changed the oxygenator in an elective way, not in like in a volatile situation. So what you have to do to prevent this trend of EMP continuity on a daily shift, you have to check the PO2 post-oxy of the patient on every shift, or not in a day once, and then calculate the gas transfer if it is the flow and the oxygenation is according to the flow or not. If it is less, then you have to change, and then you have to do the size of the membrane. The size of the membrane means when you are running continuous the machine. So there is a chance of condensation in the membrane because the continuous motor is running, and that is going to block your membrane, and there is a chance of the stuck of the oxygen and is not diffusing properly. And then you have to do the side. You increase the sweep gas flow so that the gas flow is going to push all the water from the oxygenator to the floor, and your membrane will be free from the water, and then you will find the color change in your the tubings. So normally we are using the Mackie oxygenator, and we can use different oxygenator. But for the Mackie, we have the flow chart with us. This formula is for all oxygenators, the post-oxy content minus pre-oxy content, because present pump flow into 10. This is the formula, as the fixed formula. If your result is 200 and above, we are okay with the same flow. If it is less, then we have to change the oxygenator. Then leave this. Normally, this is what we already showed you in the previous. So, only that's what this is going to. So, normally, what we are doing here is we are doing in a BB, we are doing a phantom cannulation and phantom jugular cannulation. This is our routine frequency of the cannulations. So, the first priority is we always go with the phantom, and sometimes we use the phantom. So there is a third cannula. We have the Avalon, or we can say dual lumen cannula, which is going to be inserted to the jugular, and this cannula works as access and even the return part also. So the positioning of your return is, especially the access is toward the tricuspid valve, suck the volume, and the return is toward the tricuspid valve, sorry, and so that we can provide the oxygenated blood to the heart, and it will pump to the lungs and oxygenation take place, and the sucking through the IVC-SVC. So see the position, this is access, we are getting from the tip in the IVC, and this is SVC, and this we will find out the hole here. See the return canal, the position of this one is toward the tricuspid valve. See, this is the actual position. You will see we are sucking from here, we are sucking the taking blood, and we are returning back to the tricuspid. So types of how it works will come. This is the very important purpose, the part of the slide for the whole this presentation. The pump magnet couples with the RPM of 5,000 RPM, and we pull the blood into the center of the pump. Low pressures. Normally, if you have the cup of coffee, I know 1 minute left. Cup of coffee, stir the coffee. You will see in the center, you will see something holes coming. So the centrifugal pump mechanism is in the center. We have the negative pressure, but the outer edge is the positive pressure. This is the actually mechanism of the centrifugal pump. When pump, the motor and the magnet couple together, it starts centrifuging, and you will get some revelation per minute with the help of the motor and the magnet. And they create a negative pressure in the center and positive pressure in the outer layer of the body. So this is the reason our center part we are sucking blood from through the access chamber, and the outer part we are returning back to the. But in case there is a collusion, it will not going to be blast. But if you are using the roller pump and there is a collusion, it will going to blast. There is a chance of rupture of the. But the centrifugal pump is the very safest pump. So in case of blockage, it will not going to be ruptured. See, this is the see, this is the one. See, we are sucking with the negative pressure is here and positive pressure is on the edges, and it get out of the room to leave the place. So this is the reason we will blood out. And in case we block, it just rotate. It will not do anything. There's two type of man-made lungs and Allah-made lungs. So what is the difference between the God-made and the man-made? See, the man-made lung, the body surface is only 0.6 to 4 meter squares. Limited, we have some limited numbers. But here, the body surface of the natural lung is 70 meters square. The thickness of the membrane is only 0.5, but the thickness of the man-made is 150 micron. The maximum transfer capacity with the natural lung is 2 liters per minute, but the man-made is only 4 to 600 liters per minute. This is a huge difference, which was made by the man and which is the natural lung. What is the oxygenation factors will come up? Number one, if there is a machine factor and the patient factors. What are the machine factors? The machine factors are surface area. Sometimes you are a huge patient, but you are using the small oxygenator, you will not be able to oxygenate the blood. Number two, the thickness of the membrane. Material, normally we are using the polymethyl pentene, and the blood flow, and the force bridge FiO2, and the TMP. This is the factors by the machines. The factors by the patients: hemoglobin hematocrit, your volume, after volume, temperature, sedation, temperature, and dissolution of the oxygenation. So normally we are using, how do we eliminate the CO2? With the help of in the air mixture, we have two compartments. The first compartment is for the FiO2, fraction inspired oxygenations, where we increase the percentage of like 10, 20, 30, 40, 50% normally. But for the BBM, we always be 100%. With the help of the sweet gas, we remove the CO2, and the limitation of the sweet gas is 0 to 11 liters per minute. So if you, for example, your PCO2 is higher, you can increase your sweet gas to reduce the the most important, the safety in the Ecmo, we have this the bedside. Headband, it is also the bedside. The conclusion is need a safety, Ecmo is possible, Ecmo can save the patient's life, and you should learn how to evaluate the patient and how to work with the Ecmo. Thank you so much.
Thank you.